Hello and welcome to our channel Learn at 7:30 p.m. with your friend. Relations and Functions Part 2. Before watching this video, make sure that you have watched Part 1. In today's video, we will discuss number of relations. Number of relations. Okay, we know that to write a relation, we need two non-empty sets. Let R be a relation from A to B. In this topic, we will discuss how many relations are possible from A to B. We know that according to the definition of a relation, every relation is a subset of A cross B. Or in other words, number of relations will be number of subsets of A cross B. Now, how many subsets are there for A cross B? That is nothing but 2 raised to number of elements. 2 raised to number of elements in A cross B. Okay. So number of subsets of A cross B is equal to 2 raised to number of elements in A cross B, which is equal to 2 raised to. How many number of elements in A cross B? Number of elements in A cross B is equal to n of A into n of B. N of A into n of B. Let us take n of a is equal to m and n of b is equal to n. So 2 raised to mn subsets are there for A cross B. Therefore, number of number of relations from A to B is equal to 2 raised to mn, where m is equal to n of A and n is equal to n of B. Okay. Why it is possible? Because every relation from A to B is a subset of A cross B. So number of relations possible from A to B is equal to number of subsets of A cross B, which is equal to 2 raised to number of A into number of B. For convenience, we can take it as 2 to the power m into n. Let us take an example. Let A is equal to, say, A, B, C, and B is equal to some E, F. How many relations are possible from A to B? So we can write like this. Number of relations from A to B is equal to number of subsets of A cross B. Okay. So which is equal to 2 raised to number of A into number of B, which is equal to 2 raised to what is n of A cardinal number? It is 3 into cardinal number of B, or n of B is equal to 2. So 2 raised to 6. So it is very clear that 2 raised to 6 subsets are possible for A cross B, which is equal to number of relations from A to B. Or in short, we can say number of relations from A to B is equal to number of subsets of A cross B, which is equal to 2 raised to n of A into n of B. Clear? Now moving on to the next topic. Here we will discuss different types of relations. Okay. First of all, we will discuss about universal relation. Universal relation. As the heading suggests, it's very clear. Universal means the entire. Okay. So for that, we will consider two sets. A is equal to, you can take A, B or X, Y or MN or whatever letter you want to take. Okay. So A is equal to, let us take 3, 7, 10. And B is equal to, okay, we'll take 5 and 2. Okay. 5 and 2. So we'll take a bigger number here, 13. 13, 7 and 10, and here it is 5 and 2. Now I'm going to define a relation R is equal to ordered pair AB such that A must be greater than B. Look at here. A and B are two non-empty sets here. It's given. First one A is equal to 13, 7, 10, and B is equal to 5 and 2. We have defined a relation R is equal to ordered pair AB such that A greater than B, or the first element must be greater than the second element. Fine. So before that, for whatever be the question, first of all, we have to write A cross B. If the relation R is from A to B, we should write A cross B. Cross product, okay, or the Cartesian product. Let us write A cross B first. So A cross B is equal to, first ordered pair is 13, 5. 13, 5. Second is 13, 2. Write in order always. Okay. The next one is 7, 5 and 7, 2. And the last one is 10, 5 and 10, 2. Fine. So this is our A cross B. First step is over. Now what about the second step? According to the given condition, R is equal to all the ordered pairs AB such that the first element A is greater than the second element B. So let us see R is equal to, this is the set builder form. Let us write in the listed form R, AB. So which are the function, which are the ordered pairs that we have to choose? First element must be greater than the second element. First one is okay. 13 is greater than 5. So 13, 5, this also 13, 2, this also 7, 5, this can be 7, 2 also. The here also first element is greater than the second element. Here also the first element is greater than the second element. Here you can see both R and A cross B are equal, or in other words, a relation R from A to B is said to be a universal set. A relation R from A to B is said to be a universal relation, not set, universal relation if R is equal to A cross B itself, or R contains all the elements of A cross B. That is why it is called a universal relation. Clear? Fine. Next one is void relation. Void relation. We have studied void sets, isn't it? So void means empty. So can you say what will be the definition? Void means the relation is empty, or a relation R from A to B is said to be a void relation if R is equal to 5, or if R contains no elements, then you can say it is a void relation. In the previous example, here A is equal to 13, 7, 10, and B is equal to 5, 2. So here R is those AB such that A greater than B. And we will define another relation, say R1 is equal to AB such that A is lesser than B. Can you find any ordered pair in A cross B? There is nothing. There is no ordered pair which obey the rule A less than B. In such relation, here R1 is equal to, here R1 is equal to 5, or you can say there is no ordered pair obey the rule AB such that A is lesser than B. Lesser than or greater than? Yeah, A is lesser than B. So this particular relation is a void relation on this A and B. So how can you define a void relation? A relation is said to be a void relation if R is equal to 5, or R contains no elements of A cross B. Then R is a void relation from A to B. Okay, next one is identity relation. Okay, next one is identity relation. Next one is identity relation. So a relation, I'll take it again, AB. Okay, a relation from A to B is said to be an identity relation if R is equal to A for all A in A. So here A, and instead of A and B, we can take A to A itself, okay? Because suppose we are defining a relation on set of real numbers, then both the domain and codomain are same, real number system itself, okay? So let us take an example. Let A is equal to, again let me take 1, 2, 3. And what is A cross A? A cross A is equal to 1, 1, 1, 2, 1, 3. Must put comma here also. then 2 1, 2 2, 2 3, and 3 1, 3 2, 3 3. Fine. Now I want to define a relation. R is equal to 1 1, 2 2, and 3 3. You can say this particular relation is an identity relation. So identity relation is defined as R is equal to ordered pair AA such that A in A. Clear? This is called identity relation. Next one is called the inverse relation. Okay, so how will you define an inverse relation? Let R is a relation from A to B, then the inverse of R is a relation denoted by R inverse will be from B to A. Once again, if R is a relation from A to B, then the inverse of R is a relation defined from B to A. Let us take an example. Let R is equal to AB, GI, and CK, something like that. Okay. Then how can you define R inverse? R inverse is equal to AB will change to BA, GI, IG, and CK as KC. The ordered pair, the order will be changed. Or you can say if R is a relation from A to B, then the inverse of R, denoted as R inverse, is a relation from B to A. So you can note here the domain of R will change as the domain will change as the range of R inverse. The range of R will change as the domain of R inverse. Okay, this is the method here. So I hope you got all the points that we have discussed today. Okay, so if you have any doubt and any clarification, you can comment in our comment box. Thanks for watching. We will meet with another video. Thank you.